Okay, during the first 5 classes, we were talking about the topics from Unit 1. And what we're going to start now in Class 6 is the first 4 topics from Unit 2. Okay, and we're going to break it down so that most of what we cover in Class 6 will be dealing with electrostatics. And then we'll move into current electricity, circuits, and magnetism, electromagnetism, all those things that are topics in Unit 2. So to get started, just a little bit about electrostatics, and we're going to follow the same format that we've been using since the beginning. I'm going to go through the topics first, give you a brief explanation of some of the terms and some of the types of problems that you're going to see, some of the formulas that you're going to need, etc. And then we'll take a look at some questions that have appeared on past public exams. So let's get started with electrostatics. First of all, in order to understand electrostatics, and by the way, electrostatics just means electricity that's not moving, essentially. But electrostatics is all due to the structure of the atom. So let's just very quickly talk about that. First of all, the atom, of course, has a nucleus surrounded by an electron cloud. And that's essentially what it is. Anyway, and the nucleus is very, very small, very dense center of the atom. Most of the atom's mass is in that nucleus. And it contains 2 types of particles, protons and neutrons. And the electrons are found outside the nucleus. And mass-wise, that makes up for very little of the mass. Less than 1% of the mass of an atom comes from its electrons. The vast majority of it is packed inside that nucleus. However, when it comes to the size of an atom, the electron cloud takes up most of the atom's volume, most of the atom's space. And, of course, that's where the negatively charged electrons are found. Now, what you need to remember is that atoms are electrically neutral. Now, what that means is they have the same number of positively charged protons and negatively charged electrons. And when an object gains or loses electrons, it becomes what we call an ion, and it becomes electrically charged. But atoms themselves are electrically neutral. Okay, those protons, those positively charged protons, they're locked inside the nucleus. They can't get out unless it's some sort of a nuclear reaction, which we'll talk about in Unit 3. But for all intents and purposes, when it comes to charging materials, the protons do not go anywhere. They stay locked inside the nucleus. Only the electrons move. Okay? That's probably the most important thing in this part of this topic. That's the thing to remember. Protons do not move, electrons move. Because electrons are outside the nucleus and they're kind of free to move around a bit, they're the ones that move from one place to another. Okay? Electrons do not do that. They cannot do that. Or sorry, protons don't do that. They can't do it because they're locked away inside the nucleus. So electrostatics then, in order to charge an object, we have to move the electrons around. So an object becomes negatively charged when it gains electrons. That's the key. It gains electrons. That means it now has more electrons than protons. So just for argument's sake, let's say it initially had 4 protons and 4 electrons. Okay, if it gained 1 electron, now it has 5 negative charges but only 4 positive charges. So the charge would be -1. Okay, and when that happens, we say the material has an excess of electrons. In other words, the number of protons and electrons are not balanced anymore. There's an excess of electrons. That gives us a negative charge because we got more electrons than protons. The opposite of that would be positively charged, and that occurs when there are more protons than electrons. But that doesn't happen by adding protons, because they're locked away, remember, inside the nucleus. It happens by removing electrons. If we remove electrons, we go back to our original example that I mentioned. Let's say we had 4 protons and 4 electrons. If we wanted to give that object a positive charge, we would take an electron away. And now we still got 4 protons, but now we've only got 3 electrons, which will give us a net charge of +1. Okay? We call that a deficiency or a deficit of electrons. When there are less electrons than protons, we call that a deficit or a deficiency. Now, the most important thing to remember is right down here. Please do not, okay, because this will be wrong right away. Do not explain a positive charge on an object by saying it gained protons. That is impossible. The protons do not move. They're locked away. So please don't make that mistake. If you get a positive charge, that means you have lost electrons, not gained protons. Doesn't work that way. Now, some materials can gain and lose electrons more easily than others. Okay? Some materials allow electrons to move very easily. Conductors, for example, which are pretty much exclusively metals, are made up of atoms that have very loosely bound electrons. Okay? In other words, the electrons can easily be stripped away. And examples of that would be silver, copper, aluminum, and we call those conductors. And they're also very good conductors of electricity for the same reason. Then we've got the opposite of that, which would be insulators. And these materials have tightly held electrons that are not so easily transferred. Now, it is possible to make them transfer. It is possible to do that. But there are certain ways that you have to do that, and we'll talk about those in just a second. So some examples of insulators would be things like plastic and glass, wood, rubber. Now, that doesn't mean you can't charge plastic or rubber, because you can. What it means is it doesn't happen easily. You have to do something to make it happen. So let's take a look at what some of those things are. But first of all, let's talk about the law of electric charge. And the law of electric charge essentially just says this, that opposites attract, and you've heard that expression before, opposites attract. But opposites attract each other, opposite charges that is, and like charges actually repel each other, push each other apart. Whereas a charged object will attract a neutral object. And we'll talk more about that one in just a minute too, because charged objects attracting neutral objects are more like opposites attract, and we'll talk about why that's the case now in just a couple of minutes. In order to detect electric charge, we use a device called an electroscope. And there's lots of different designs for electroscopes. Okay, the most common one is what we call a metal leaf electroscope. And that's what you see there. And essentially all it is a glass flask, and we use glass because glass is a good insulator. And then we have a metal rod with a metal ball on top and 2 thin metal leaves down at the bottom. So what happens is if this electroscope becomes charged, then the 2 leaves become like charges. They might both have a positive or both have a negative charge, and they'll repel each other. And by repelling each other, they'll actually spread apart. So when they spread apart, we can detect that the object now has an electric charge. There's another type of one called a pith ball electroscope, P-I-T-H. And really what it is almost like little styrofoam balls with a metallic coating on them. And that serves exactly the same purpose as this. If the balls become lightly charged, they spread apart. And the bigger the charge, the further they spread apart. Simple as that. Okay, so that's what an electroscope is. And it can detect charge because if the leaves become like charges, they repel each other and they move apart. Now, because everything is connected and everything's a conductor here, it's impossible in a metal leaf electroscope to have an opposite charge on each leaf and for the leaves to attract. That can't happen. It's impossible. They always will have the same charge or no charge. If they have no charge at all, they'll just hang straight down. But if they do have a charge, then they will spread apart. The stronger the charge, the further apart they will spread. Okay? So that's how an electroscope works. Now, if we want to charge an object, there's three ways to do it. Three ways to charge. We can charge by friction or by rubbing, and you've all done that before, I bet. Everybody, I don't know many people who haven't done this, take a balloon, rub it on your head, and stick it on the wall. Okay? Not many people haven't done that. That is charging by friction. Or if you take a wool sweater and you pull it off over your head and you get all this static, your hair starts to get all staticky. Okay, that is charging by friction because the two are rubbing against each other. The wool sweater is rubbing against your hair. Okay, that's what we call charging by friction. Then there's charging by contact, which is sometimes called conduction. Then there's charging by induction, and we can do that with no contact or with a special type of contact. And we're going to talk about all those types now in a minute. So we got friction, conduction, and induction are the three basic ways to charge an object. So let's look at charging by friction first. The two objects somehow have to rub together. Now when we do that, there's no charge being created or destroyed. All that's happening is electrons are being transferred from one material to the other. Okay, the total number of electrons doesn't change. The total number of protons doesn't change. But the number on each object does change. Okay, we actually move from one object to the other. So charge is actually conserved, the total charge. So if one object loses 50 electrons, then the other object has to gain those 50 electrons. Okay, they have to go somewhere. They're not destroyed. So let's look at that in a little more detail. When we charge things by friction, we use something called an electrostatic series in order to determine which material gains electrons and which one loses electrons. In this electrostatic series, we can actually look materials up and tell which one has the stronger attraction for its electrons. Because some materials hold on to their electrons more strongly than others. Just like two people in a tug-of-war. Okay? If one person is stronger, they can pull harder. Well, it's kind of the same thing as that. Okay? The stronger ones hold on to their electrons more tightly, and the weaker ones not as tightly. So if a stronger one and a weaker one are rubbed together, the one with the stronger attraction will start to pull electrons away from the weaker one. For example, the balloon rubbed on the hair, the example we mentioned there a few minutes ago. A rubber balloon, hair is a lot like cat fur, very similar composition. So we got rubber and we got hair or fur. If you look at the electrostatic series, it tells us that at the top we've got a weak attraction for electrons, and as we move to the bottom we have a strong attraction for electrons. So in this particular example then, in this example, because rubber is lower on the electrostatic series, that means rubber has a stronger attraction for electrons than fur or hair does. So if you rub the rubber balloon on your hair, because rubber attracts its electrons more strongly, it's actually going to steal electrons from the hair or from the fur. So that means the rubber will actually end up negatively charged because it will end up with an excess of electrons. And because the hair or the fur loses electrons, it will actually become positively charged. Okay, whatever electrons are lost by the hair will be gained by the rubber. So the hair loses electrons to the rubber. The rubber becomes negatively charged, the balloon becomes negatively charged. That's why it sticks to the wall. Because negatively charged objects attract neutral objects, or are attracted to neutral objects. And we'll talk about why that is now in just a sec. Here's the second one, charging by contact, or conduction. So we got an electroscope here. Before anything happens, it's neutral. And you can see it's neutral because the leaves are hanging basically straight down. And if we counted the number of positives and negatives all over this electroscope, we'd see that they balance out. Same number. Now what we're doing is we're taking this electroscope and we're touching it with a positively charged rod. Okay, more positives than negatives. When that happens, electrons are actually attracted from the electroscope into this rod. Because when you charge by contact, both objects will end up with the same charge at the end. So you touch this positively charged rod here, That pulls electrons away into the rod and leaves the rod with a deficit of electrons. But this positively charged rod also still has a deficit of electrons. It's not as big a deficit as it was before, but it still has fewer electrons than protons. So it still has a positive charge, just a lesser positive charge. But now the electroscope, because it lost electrons, also has a positive charge. And if you look down at the bottom, these two leaves now, because they're positively charged, are repelling each other. And even after that charged rod is removed, those electrons now are gone. They're not getting back, unless you do something else. But right now, you have what we call a residual charge. In other words, the charge stayed after the object was taken away, because we touched it. Because we touched it. So that's what we call charging by contact. And this stuff should be just reviewed for you. I'm just very quickly going through it. Then we have induction. So when we charge by induction, it can be temporary or it can be residual. Let's look at temporary first. For temporary, initially we have a neutral electroscope. When we bring this positively charged object close but not touching, it's not touching. Okay, that's the important thing. When you charge by induction temporarily, there's no contact whatsoever. Nothing touches the electroscope. So it's brought near. When it's brought near, what happens is electrons are attracted to that positively charged object because opposites attract. So electrons start to move up to the top to get closer to that positively charged object. Because the electrons go up towards the top, that leaves the top of the electroscope with a negative charge, but the bottom of the electroscope actually has a positive charge. So it's actually different at both ends. That's the unique thing about the induction, temporary induction. Okay, so what's happening is the electrons are leaving the leaves, going up there to get close to this positively charged rod. So temporarily we have a negative charge on the top, we have a positive charge on the bottom, but it's only temporary. Because as soon as you take this positively charged rod away, what happens is now we have all those electrons that were attracted up here in the first place, they end up going back down again. They go back down to the bottom, and now our electroscope is just going to be negative all over. Okay, or sorry, neutral all over, I should say. Okay, the charge now is gone. But see, it was never really charged in the first place. It was only a temporary redistribution, is all it was. This is why positively charged objects are attracted to neutral objects, because in the neutral object we get a temporary redistribution, and now right here you got opposites attracting, right? Because you got negative charge on the top of the electroscope being attracted to positive charge on the charged object. That's why charged objects attract neutral objects. But like I said, as soon as we take this object away, the electroscope goes right back to the way it was before. Right back. The thing is, it's a temporary charge. It's only temporary. Okay, it goes back to normal as soon as you leave it. That's different from a residual charge. That's different from a residual charge. Okay, in a residual charge, we do the same thing. We take our positive object, we bring it close, but we don't touch. Again, we're not touching. And that pulls electrons up towards the top. Okay? Then what you do is you ground the top of the electroscope. You ground it. And when you ground it, here's what happens. Here's what happens. Instead of pulling electrons up from the bottom of the electroscope, they come from the ground instead. Okay, so what we're doing now is we're actually pulling electrons from the ground, and the ground can be something as simple as touching it with your finger. But we're pulling electrons from the ground into the electroscope. Then what you would do is you remove the ground after those electrons have moved, and once you do that, now those extra electrons are trapped in the electroscope. So what you've done is you've given your electroscope a residual charge, but it's a negative residual charge. Even though the object that was involved was a positively charged object, the residual charge that you ended up with is a negative charge because the positively charged object pulled electrons out of the ground into the electroscope. So that's the important thing to remember here. When you charge by contact, you end up with the same charge, but when you charge by induction, you end up with the opposite charge. Okay, that's important to remember. That's important. Let's look at some examples. Some examples from old public exams. So the first one says, what happens to a neutral electroscope when it is briefly touched by a positively charged glass rod? Well, I just told you that when you charge by contact, the object will end up with the same charge as the initial charging object. So a positively charged glass rod will give the electroscope a positive charge. And remember, an object becomes positively charged when it loses electrons. It has to lose electrons in order to become positively charged. It has to lose electrons in order to become positively charged. All right? Second one. This time it says a neutral electroscope becomes positively charged after it is briefly touched by a charged rod. Okay, it's basically the same thing we just talked about. Which explains that flow of charge? What happens, in other words? What happens is the electroscope loses electrons because the positively charged rod actually pulls electrons out of the electroscope. So electrons flow from the electroscope to the rod. Now, right away, as soon as you see gain protons, lose protons, you know that doesn't happen. You can discount those immediately. Same thing down here. Protons do not move. Remember that. Protons do not move. So electrons move. So in the second one, then, it's had to be either A or B, but B is no good because if electrons flowed from the rod to the electroscope, if electrons flowed from the rod to the electroscope would have ended up negatively charged. Okay? Not positively charged. So that wouldn't work, in other words. All right, the last one down. Which describes a neutral electroscope after it's briefly touched by a positively charged rod? Positively charged rod. What happens is, after you touch it with a positively charged rod, it's not near, it's actually touched. As soon as it touches, now the neutral electroscope has become a positive electroscope. And that means that the top of the electroscope is positive and the bottom of the electroscope is positive. It's positive all over. When you charge by contact, you have the same charge all over. When you charge by induction, okay, when it's temporary, it's a different charge on top and bottom. But that's only if it's close to but not touching. In this case, it did touch. Okay, it did touch. It says there it was touched. Next question. Kind of a logic problem. The diagram below shows 4 neutral spheres, W, X, Y, and Z, on insulated stands with W touching X and Z touching Y. And you can see that right here. These two are touching. These two are touching. In the middle, there's a positive rod. Now, we need to know what's happening when that positive rod is there. That positive rod is attracting electrons in all of these spheres. So what happens is this. The electrons are getting pulled closer to the positive rod, which means electrons are getting pulled from W into X. So electrons are actually going this way. And same thing here. Electrons are getting pulled from Z into Y. Those negative electrons. That's what's happening. If we then separate W and X and Y and Z, if we then pull them apart, then the electrons that got pulled away from W are going to leave W with a deficit and X with an excess. And that should make sense to you, right? The electrons are moving from one to the other to get closer to the positive rod. So therefore, one now has a deficit, the other has an excess. So W because it now has a deficit of electrons, has to be positive. So we can rule out the first two. W we know has to be positive. This one is positive, this one is negative, because electrons have moved from W into X. And when we separate them, they get trapped. And over here, this one is negative, this one is positive. So W is positive, so is Z. So the answer is D. The answer is D. Let's try this one. This diagram shows a positively charged rod placed near but not touching. Near. So this is temporary induction now. It's near but not touching a neutral metal ball. Which best describes what happens to the sides of the ball? Well, this positively charged object is going to start pulling electrons over this way. The electrons are going to start moving from X to Y. So that means that this side is left with a deficit of electrons, which makes it positively charged. This side over here, Y, is left with an excess of electrons because the electrons are trying to get close to that positive rod. So what's happening is, at least temporarily, X becomes positive and Y becomes negative. Okay, X becomes positive, Y becomes negative. So we know it's either this one or this one. It's not this one or this one. X is positive, Y is negative. Okay, so we know it's either B or C. Now, is the ball attracted to the rod or is the ball repelled? Well, if Y becomes negative, then the ball is going to be attracted to the rod. And all you got to remember is the law of electric charges. Neutral objects are attracted to charged objects. They don't repel each other. The only way to repel is that they both have the same charge. So X becomes positive and the ball is attracted. The ball is not repelled. Neutral objects do not repel charged objects. Never. Last one on this page. Which one of those best describes why a plastic comb that has been pulled through here becomes negatively charged? Look, there's two here you get rid of right away. Gains protons, doesn't happen. Loses protons, doesn't happen. That simply doesn't happen. Now, if the plastic comb becomes negatively charged, the only way for an object to become negatively charged is if it gains electrons to give it an excess. So it must, A, gain electrons from your hair. That's the only way to explain what happens. The only way. Okay, here's another one. Sphere X and sphere Y are on insulated stands as shown below. X is positive, Y is neutral. And sphere X, which is positively charged initially, touches sphere Y. If X and Y are then separated again, what will be the charge on each sphere? What will be the charge on each sphere? Okay, X was positive. When a positive object touches a neutral object, now both objects are positive because the positive object pulls electrons away from Y. X pulls electrons away from Y. And when they touch, it's a permanent shift, unless they touch again. Okay, so X is still positive. X is still positive, but now Y is positive too. So it's A. They're both positive. They both become positive. That's the only explanation. So these types of questions are fairly common on the public. Now there's usually only one or two. There's usually only one or two like that in the multiple choice. And often there's nothing at all in the second part. Okay, over the last 3 to 4 years, if you go back and look over the public exams, there's only a couple of times there's been a constructed response item based on static charge. This is one of them. Let's take a look. Using diagrams and brief explanations, describe how a negative charge on a metal leaf electroscope can be produced by induction. Induction means the charged object does not touch the electroscope. It doesn't touch. So here's what we do. First thing we do is we bring a positively charged rod near the electroscope. And it's very important that it's a positive, because remember, when you charge by induction, it's always going to be the opposite charge. So if you want a negative charge on the electroscope, you've got to use a positive object to do it with. So that's the first step. And that will cause electrons to travel to the top of the electroscope because they're attracted to that positively charged rod. Then what you do is you ground the electroscope, and what that does is it pulls electrons away from the ground to get close to that positively charged object. So electrons actually leave the ground, they come up into the electroscope in order to get close to this positively charged object. Then you remove the ground first, then remove the charged object. And the order is very important, because if you remove the charged object first, then the electrons will just go back into the ground, right back where they came from, and you'll have no charge residually. The charge will just be gone, because all the electrons that came in went out again. But if you remove the ground first, the electrons get trapped. It's like blowing up the bridge. People can't get back across the river. So by removing that ground, you've taken the path of the electrons away. They have to stay now in the electroscope. So the electroscope ends up being left with a negative charge. That's the way you'd explain it. Okay, so that question was on an old public exam. Hasn't been there for a couple of years, so I wouldn't be surprised to see it again. Here's another one that talks about electric charges. We've got the diagram below. We've got a neutron, a proton, a neutron, and an electron located between two horizontally charged plates. Describe what will happen to each particle in this field. What would happen to each particle? Well, it's not that difficult. Let's look at the proton. Well, first of all, the neutron. The neutron won't move. Now, you might say, well, that's odd. I thought you said that neutral objects are attracted to charged objects. Yes, we did say that, but we said it was because of a temporary redistribution of charge. Neutral objects become temporarily charged when they're next to a charged object. That's why they attract. A neutron doesn't have any electrons to move around. The neutron by itself would not be affected by these charged plates. So the positive on the top, the negative on the bottom, wouldn't matter. The neutron is not affected. However, the other two particles are. The proton would start to move. Obviously, because opposites attract, the proton would move towards the negatively charged plate, because opposites are attracted. The electron would move away from the negatively charged plate towards the positively charged plate. Okay, because again, opposites attract, or like charges repel, whichever way you want to explain it. And then, which one has the greatest acceleration? Which one is going to move the fastest? Well, if you think about it, Newton's second law tells us that force equals mass times acceleration. Now, because protons and electrons essentially have the same charge, except opposite signs, they're really going to have the same force. So the proton is equally attracted to the negative as the electron is attracted to the positive. That's an equal force. But the other thing that affects acceleration is the mass. And the electron is actually the lighter particle, the less mass. Okay, so the proton has a higher mass, the electron has a smaller mass. Therefore, the proton will have the lower acceleration and the electron will have the greater acceleration. That's the explanation for that. They both have the same charge. One is positive, one is negative, but the magnitude of the charge is the same. But, because the mass of the electron is smaller, it's going to accelerate more quickly. And you can think about it like this. I mean, if you had a trailer behind your truck, you can't accelerate as fast as you can when you don't have the trailer behind your truck. And it's because mass affects acceleration. The more mass you have, the slower the acceleration will be. It's that simple. Okay, so that finishes up the introduction to electrostatics. In the second topic, we're going to talk about Coulomb's law and a little bit about proportionalities with Coulomb's law. Sometimes people find those to be the toughest questions because you're not really dealing with an equation, you're dealing with a proportion instead. So that's where we'll pick up in topic 2. So good luck with your study, work hard, and the more of these you do, the easier that exam is going to be.